All right. Hello, good morning. So let's check out related rates. This is a pretty big part of Calc 1, and it can be relatively challenging because it relies on so many different things. It's not just calculus. So I'm going to put that up here. It's not just calculus. And, you've heard me say this before, which is that, this course is like 99% algebra and other stuff and 1% calculus. So really, one of the least important things you'll be doing, even though it is calculus, one of the least important parts of the problem is the actual calculus. It's setting up is so much more challenging. Finding out the path to the solution is much more challenging. So that's what we're really after here. It's not just plugging and chugging derivatives like we did in chapter 2. It's really about setting it up. So what I wanted to give you today is a general strategy, which we'll refer back to. I'll walk through two relatively characteristic problems from the related rates genre, and then I'll set you loose on practicing on your own. These will be challenging. I will just say that. So don't lose faith, and there's really a great sense of satisfaction that even with help when you come to the solution of one of these, that you did something really, really cool. So first of all, why do we call it related rates? Well, usually in the real world, which, is tough to come up against in math because the real world is so complicated, but calculus is the math of change. It's the math of the real world, but in the real world, we don't have just one thing that changes in relation to another, right? There's not just a car going down a street and, it's change in distance with respect to the change in time. There's a lot more going on that we probably are interested in. The acceleration, the force on it due to the wind, fuel efficiency, all different sorts of things. How many gizmos are on in the car, etc. It's all interrelated and it's all very complicated. So we have rates of change that are related to each other somehow in a sort of like system. All right, and again, I'm just saying this so that you understand it's more than just a simple one function with one input, one output. So what this requires, since it's multifaceted, is that you sketch the situation. Even if you are you identify as not being an artist like myself, you will want to sketch it out because there's just too much info. Okay, so sketch out as best you can and then label the quantities what you know and avoid extras. And so I'll tell you what I mean by that. Avoiding extras means like if in the problem, for whatever reason, you got a beam and this beam is a length of 5 meters. This is just an example. So if this beam's 5 meters and for whatever reason we're talking about slicing it at some mystery distance x, you might be concerned about, this side over here, well, what is this length if this is some unknown length x? Well, you might want to call this y. And I'll tell you, don't do that, right? Because you just introduced a new variable that you didn't need to. Instead, think about it like this. Well, if this is x, and I know the whole beam is 5, then this length is really 5 minus x, right? It's the remainder. So when I add these two together, I'm left with 5. So you see how this keeps it in terms of one variable instead of two? This is kind of a theme that I want you to look out for. So label what you can, and then connect things via equations, often geometric. So we're talking about, area, perimeter, volume. These are formulas you probably haven't seen in a while, but you'll relearn them on the fly, so don't sweat too much. They're all pretty basic. And I want this to be your mantra here. And I mean that in terms of like what you're repeating to yourself over and over. What am I solving for? What am I looking for? This is, often when we don't really have a solution pathway, just asking yourself this question over and over can kind of help our mind drive towards things that are more connected. All right. And at the end, you're going to differentiate probably implicitly, and solve the equation for the desired rate or quantity. All right, so we're probably going to use implicit differentiation, right, which means, for if we see some y, that it's really some function of x, and that, if we differentiate y squared with respect to x, like we've done with implicit differentiation, you're going to have to use the chain rule, right? And this will often come up as a way for us to access the instantaneous rate of change or the derivative that we need. All right, so I know this is very general, but I want to frame this so that we have something to look back to when we work through these two problems. I'm going to work through two pretty standard problems so that you can see these things in action and then hopefully be able to apply them in the other practice problems you'll be up against. Okay, so here is the sliding ladder problem. This is this happens in like every calculus course. I didn't want you guys to miss out, but I'll give you my take on it. All right, so this on its own could strike fear into the heart of a math student. We're not seeing any formulas. We're not seeing any diagrams. It's just a verbal description. So we're going to walk through this guide that I just gave you over here. Okay, I'm not sure why that wasn't maximized. Here we go. So a 10-foot ladder leans against the wall. The base slides away from the wall at 2 feet per second. So the top is sliding down the wall. How fast is the top of the ladder sliding down when the base is 8 feet from the wall? So you can think about this, nightmarish scenario of a ladder falling, sliding down the wall. The base is scooting out and the top is sliding down. That's not going to be at the same rate, right? You can kind of think about how the base, I don't know, to me, just intuitively, I see the base sliding out faster than the top coming down. But it's not clear, but they are definitely related. So this is a related rates problem. So what I said first was what? Sketch it out. Sketch out whatever information you have on the system. I know there's a wall. I know that there's a ladder leaning on the wall, so there will be a floor here. And let's say our ladder is leaning here. And I know this ladder, I'm actually going to put points here at the end where it's touching. And I know that this ladder slides away from the wall at 2 feet per second. We know that the ladder is 10 feet long. That's important. All right, so that's this length, which is fixed. And I know the base slides away, so the point at which this is here slides away at 2 feet per second. So let's put that here, 2 feet per second. And the top is sliding down, and we want to know how fast is the top sliding down. So this is, moving. I'm using this arrow to represent change. And we want to know how fast is it moving here. So this is really what we're after. When the base is 8 foot from the wall. Okay, so when this base here is at 8 feet. That's pretty much all we have given to us from the verbal description. Now what we want to do is label quantities. All right, so let's label some quantities here. We can call this, big L for the length of the ladder, but this is really fixed. So it doesn't need a variable name, but we'll just give it a name. Now, this over here, we were given the rate of the base sliding away from the wall at 2 feet per second. What is this? Well, this is the speed at which this point is coming out. But another way to think about it is that it's the rate at which this length here is growing, right? Because this 8 feet is only 8 feet for a second. If this thing's sliding out, this is a growing quantity, which means it's a variable. So this here, we should really come up with a name for this, and we should call this B for the base. Let's actually use a lowercase b here. Oh my gosh. B. And this B is changing at this moment that we care about. It's at 8 seconds, which lends us to think about this as being, let's call it the variable h, because that's the height at which the ladder is up on the wall, right? And you're probably seeing, hey, this looks like a right triangle. Okay, so now I've got some things named. That's all good. Now this length b is named, but what is this rate? This is the rate isn't b. This is how fast b is changing. How do we represent how fast b is changing? The change in b over the change in time, right? So this is really db dt, if we're calling this length here b. And so that means that this rate up here is what? dh dt, and this is what we're after. All right, so I might like highlight this over here. This is what we're after. How fast is the top sliding down? Which again takes a little bit of thinking to relate that point coming down to being the same as how fast this h is changing, right? That's not immediately obvious to somebody. So let's think about now some equations that tie these things together. Equations that relate b and h. Why? Because I have this rate and I want to relate it to this rate. Okay, so what are some equations that relate b and h? Well, this is a right triangle. So let's see, we've got area is 1/2 b times h. That's pretty nice. But we don't really care about the area right now, right? That's not necessarily what's changing. And we don't have the area of this triangle. It's not really pertinent, so we might say maybe later. We also have the Pythagorean theorem, b squared plus h squared equals l squared, which would be like 10 squared here. And this directly relates b and h, and it has the fixed constant of the length of the ladder in there. So this is a pretty good starting point. So this is an equation that we can use to relate those two. Let's also note what we've done here is we've implied that b is a function of time and that h is a function of time. Implicit functions of time. Since we're talking about their rates with respect to time, that's what this means. So then what we can do then is assume this is an equation with two functions of time, b of t and h of t. All right, so what I'm going to do is grab this, come to a new page. Maybe it won't let me paste that. That's fine. So I've got this equation with two functions of time, so now I can differentiate this with respect to time on both sides. So if I have this and I differentiate everything with respect to time implicitly, then what I'm going to get is what? 2b times db dt, because b depends on time, plus 2h times dh dt, because h depends on time, equals 0, because 100 is just a constant, so derivative with respect to t is 0. All right, so now from here, let's see, what do we know? I know I'm after this. This is what we've been searching for, so that's what I meant by this piece here. Differentiate, probably implicitly, and solve for the required or desired rate or quantity. So we just differentiated implicitly, and we now have access to dh dt. It's in the equation. What else do we know? We know b at this point is a length of 8 feet. We know db dt is 2. We know that we don't know what h is at this moment, but we can go find it. And we know we're after dh dt. Why did I sound so confident that we can go find it? Well, I know that at this moment, this is at a length of 8. The ladder is a fixed 10 feet. So really, this is just a Pythagorean theorem problem, right? So 8 squared plus h squared equals 100. which means h squared is 36, so h is 6. All right, so really this is 6 here. A little cartoony thought bubble here. So that's where that comes from. And now I can go ahead and solve for dh dt. So what this is, 8 times 4 is 32 plus 12 dh dt equals 0. And then I'll solve for dh dt and get what, a negative 32 over 12, which is like negative 8/3, which is about negative 2.667 feet per second. So what does this tell us? The top of the ladder is falling 2.667 feet per second. We could say falling at 2.667 feet per second when the base is 8 feet from the wall. So, Mally, how did you know that? This is negative. So that became this word falling because I knew it's decreasing. And based on the diagram we drew, right, I said this is moving out at 2 feet per second. So that makes this the negative direction, right, if moving to the right was positive. If you drew this triangle like this instead, your answer might be the opposite. So just to be aware of that your setup to these really matters, your orientation. But so that's what this ended up meaning. dH dt is this negative 2.667. This is what we would interpret that to mean. And I just want to quickly run through that process of how we got here because it might have been pretty quick for you. So first we sketched the situation. Got it, right? We brought up the ladder leaning on the wall, our measurements that we knew at that moment, the rate that we knew, what we were after. And we labeled quantities as best we can. We said, well, it makes sense since this is changing and this is changing to give them variables. We know this is fixed, so we can just keep it as 10. And then we named the rates based off of those variables. And then in so doing, assumed that they are implicit functions of time. Okay, so that happens a lot. Then we connected them via equations, often geometric. We looked at the area formula. We said that's no good, but this one relates B and H together. And we can differentiate them now implicitly and solve for that quantity. And that's what we did here, right? We got that equation set up with B and H. We differentiate with respect to T and then solved for H. Now, something I see happen a lot is people will plug in what B is here already and then differentiate. And then you'll just get 0, right? So if that happens, know that you plugged in too soon. You still need that variable of where the quantity's at. So differentiate it in general with respect to time first, and then plug in the values that you know. You see how I waited to do that until here. So I'll say wait to substitute. All right, and then we went in and solved for that value. We noted what that sign really meant and then interpreted that rate based on our setup. Okay, so again, that's a classic problem because it highlights all the different pieces pretty easily. Let's look at one that's a little bit more complicated. All right. Oh, let me erase this stuff real quick. All right, I had previously recorded this with no microphone on. Classic. So let's try it again. So a water tank has the shape of an inverted right circular cone of height 12 and base radius 6 feet. The water is being pumped into the tank at a rate of 10 gallons per minute. Approximate the rate at which the water level is rising. Okay, again, seems like you don't have much to go on until you get a sketch going. All right, so a conical tank used a lot in making wine and fermenting beer, things like that. Let's draw out a cone. We know that this has a height of 12 and a radius of 6 feet. Water's being pumped into the tank, so I'll use blue to kind of pump in over here at a rate of 10 gallons per minute. So that's H2O. And let's approximate the rate at which the water level is rising. So we have a water level in here. And we want to know the rate at which that's rising when the water's 3 feet deep. Okay, so when it's 3 feet, how much is this rising? And so we're talking about this value changing, and so that will be in what, feet per minute? Okay, so and we want to know what that is. So let's go ahead and label some things now. We've kind of grabbed all the information from the text. Now let's start to relate things together, see what we've got. So, all right, 10 gallons per minute. This is coming into the tank and giving us this volume of water in here. This is a volume of water, so I'm going to use V to represent that volume of water, which is changing, right? So the volume is unknown. At this moment, you could go in and calculate it, but we're going to pause on that for a second. So let's see what we've got. Well, the water is changing 10 gallons per minute. So we know that dV dt then, the rate at which the volume is changing with respect to time, is 10 gallons per minute, which if we want, and we've been given here this conversion rate, this is really what, 1.337 feet cubed per minute. So we can keep everything in terms of cubic feet. All right. So the volume is changing at a constant 1.337 feet cubed per minute. And so we know that. Let's put that in over here. 1.337 feet cubed per minute. We're looking for the height that's changing here. We know it's 3 feet at this moment, but we should note that it's changing, so we're going to call it H. All right. So that H is changing, but we want to know how fast it's changing. So then what would we call this? dH dt. And this is getting a little crammed in here. dH dt is what we are after. Okay? So that's what we're after. Now we kind of need some, that we've labeled some things. Now we need some equations to relate these things together. So, you know, what relates H to V? Well, there's a couple ways to think about this, but for a cone, we know that the volume is given by pi over 3 r squared h. You say, Mally, I didn't know that. I don't know if I've ever learned that. You probably have, but you probably forgot it. So that's okay. But I'm giving it to you now. So the volume of a cone is given by this. Now this is helpful, but what's tough is that the radius and the height are both changing. All right. So one way you could do this is by differentiating it with respect to both r and h, using the product rule and thinking that they are both functions of time. So you could think, you know, r is a function of time. The radius of what? And yeah, and what are we talking about? We're talking about the radius of the cone of water, right? There's this cone of water sitting inside this big fixed cone, and this is the cone that's changing, right, in here. So this cone is changing, the radius is changing, and the height is changing. All right, so I just introduced a new variable here, the radius of the cone of water. So this is a function of time, and h is a function of time. Now, what I'm going to recommend that we do here is you can eliminate one of the variables by using another geometric relationship. So if we note the problem that we have, can we eliminate r so that we just worry about h? Because we want dh dt. That's what we're after. So one way you can do it is look from the side, what we call a projection of the cone. This becomes a two-dimensional view of this, where you've got now a triangle of water sitting in a triangle that's a bit bigger. This triangle has that half base is 6 and the height is 12. And what we see is that inside this big triangle we have a similar triangle. Mally, what do you mean by similar triangles again? I mean that this angle is the same as this angle. These angles are shared. And obviously this one here, this right angle, is shared. So we have this, let me do a highlighter here. So we have this triangle in here that these two are similar, and which means that their sides and angles are related. So since the angles are the same, the proportion of the sides is the same. So if we call this h, which is changing, and this r, which is changing, we know that r is to h as 6 is to 12. Okay, so what does this do? This gives us a second equation that allows us to eliminate r by solving for h in terms of r, or r in terms of h, rather. I misspoke there. So go ahead and solve this. You get 12r equals 6h. So that means that r in terms of h is 0.5h, which you might have seen just from looking at this diagram, right? The radius is half of the height for the triangles set up in this way. So if r is 0.5h, we can now feed that back into our original. V equals pi over 3 r squared, which we said is 0.5h squared times h, which then altogether here is what? 0.25 over 3 times pi times h cubed. All right, so if v is all this 0.25 pi over 3 h cubed, you could take this to a decimal here, but let's not worry about that right now. Now what I can do is differentiate both sides implicitly with respect to time, because I know v is a function of time, h is a function of time. And so we'll get dv dt equals this thing, 0.25 pi over 3, this coefficient, times 3 times h squared times dh dt. See how that happened again? That now, since I differentiated implicitly, I now have access to the rate of h with respect to time. And we said we know that dv dt was 1.337, right? That equals this times 3. Well, the 3's are going to cancel, so let's just go ahead and deal with that right now, right? Times h squared. Well, what was h? We said h at this moment was 3 times dh dt. I don't know why I'm writing so crooked right now. Try to fix that. All right. So now we can go ahead and just solve for dh dt. So dh dt equals this 1.337 all over 0.25 pi times 9. And so what do we get there? So we get 0.1891. Can quiz yourself on what are the units of this quantity. It's going to be feet per minute, right? dh dt. And so what does this tell us? This tells us that when the height of the water in the tank is 3 feet tall, 3 feet high, water is rising 0.1891 feet per minute. Is that constant? Is that a constant? Will that always be the case? No, definitely not. If the volume is constant, right, the radius is not changing at the same rate the entire time, right? As you get taller and taller and you're pumping in the same amount of water, that's stretching out further and further over this radius. So that is changing. So that's why it's important to say the moment that it's happening. When the height is 3 feet high, then the water is rising at this amount. Okay. So again, I'll leave it to you to kind of pause and replay to go through this and seeing the different parts of this general strategy I gave you, which are sketch, label, find some geometric equations, maybe a couple of them, like we did with that last one. Note constantly what you're solving for, and then probably end up using implicit differentiation to solve for the rate that you need. So again, remember that last part is that 1% calculus, and everything else is the challenging bit, the algebra, problem solving, thinking it through, and being creative. All right. There's a lot of videos out there that can help you with these, and I encourage you to watch some of the more popular ones. But in general, coming back to this as our general strategy will serve you best. All right. So I hope you have fun. I look forward to your questions in the class discussion. Lean on each other. Lean on me for help here. And again, enjoy the challenge, because once you get to a solution, even with some help, you can really be proud of yourself for sticking with it. All right. Do your best. We'll see you out there.